In section 1.7, we're going to introduce the topic of linear independence. So, in order to think about linear independence, we are going to talk about homogeneous systems that we introduced in section 1.5. So the following is a homogeneous system because we have a matrix A, a vector x, and this is equal to the right-hand side is the 0 vector. And note that we can write any matrix equation like this as a vector equation where we think about the columns of A multiplied by the variables in our x vector. So we have x1 times the first column, 1, 3, 5, plus x2 times the second column, plus x3 times the third column equals the 0 vector. In 1.5, we talked about how every homogeneous system has the trivial solution. That is, x equals 0 is a solution. That's because if I plug in x1 equals 0 here, x2 equals 0, and x3 equals 0, that is trivially going to give us a true equation there. 0 is going to cancel out everything on the left-hand side. We're going to get 0 on both sides. But that's not interesting, and we want to ask the question, is that the only solution? Or is there some solution here that also gives us 0, 0, 0? That's a little more interesting. So now let's look at what it means to be linearly independent. We say that a set of vectors, v1 to vp, in Rn is linearly independent if the vector equation, like we just had on the previous slide, x1 times a vector plus x2 times a vector all the way to xp times a vector is equal to the 0 vector, has only the trivial solution. So when we're talking about linearly independent, we are saying that the homogeneous equation has only the trivial solution. So the homogeneous system has only the trivial solution. There are no non-trivial solutions if we have linear independence of those vectors. The opposite of linear independence is linear dependence. We say that a set of vectors is linearly dependent if there exist weights C1 to CP. Those are numbers, constants, numbers, not all 0, such that C1v1 plus C2v2 all the way to CPvp is equal to 0. This is what we call a linear dependence relation, when the weights are not all 0. We can think that this C1 to CP is a non-trivial solution to the homogeneous equation. As long as C1 to CP are not all 0. You could have some of them be 0, but at least one entry has to be non-zero. And this is what we call a linear dependence relation. So thinking about section 1.5, we talked about the difference between only having the trivial solution and having non-trivial solutions. Now we're going to say that this is similar or exactly the same idea as the vector equation corresponding to linearly independent vectors or linearly dependent vectors. So let's look at the example that we mentioned on the first page. We have 3 vectors here. This was the columns of A that we had before. 1, 3, 5, 2, 5, 9, and negative 3, 9, 3. We are going to determine if these 3 vectors create a set that is linearly independent. Note that when we say is the set linearly independent, that's one object, so we say is. We could say that v1, v2, v3 are linearly independent vectors. If we do find that they're linearly dependent, let's find a dependence relation among them. So to find this, we're going to again look at the augmented matrix. We're going to row reduce, and we're going to look at the solution to that augmented system. So let's first look at the vector equation that we introduced on the first page. x1 times the first vector plus x2 times the second vector plus x3 times the third vector equals 0. We are trying to see, is there numbers x1, x2, x3 that we can plug in not all 0 that satisfy that equation, trying to find a solution to that system. So we can look at the augmented matrix here. We have our 3 columns, give us the first 3 columns are augmented matrix, and then 0 on the right-hand side, since this is a homogeneous system. If we row reduce, we can get to this matrix over here. This is in row echelon form. We can get there by doing the row operations, -3 row 1 plus row 2 into row 2, and also -5 row 1 plus row 3 into row 3 to zero out these 2 entries. And then to get a 0 in this entry, we can do negative row 2 plus row 3 into row 3, and we get a row echelon form, not reduced yet, but a row echelon form of 1, 2, -3, 0, 0, -1, 18, 0, and a row of zeros on the bottom. If we look at this matrix, we can identify the pivots. We have a pivot in the top left corner, we have a pivot right in the middle, and we have our third column represents a free variable, as there is no pivot in that column. In the previous lecture, we said that a free variable means that there are non-trivial solutions. So since x3 is a free variable here, we know that there exist non-trivial solutions. Therefore, another way of saying that is that the set of vectors v1, v2, v3 is a linearly dependent set. The existence of non-trivial solutions to a homogeneous system is what we're going to define as linearly independent or linearly dependent. And note that if I want to find a particular linear dependence relation, which we're going to do in part B, I don't need the row echelon form, I need the reduced row echelon form. So before we move on to part B, let's find that matrix. No matter what row operation I do, column of zeros is just going to stay a column of zeros there. I'm going to keep the zeros, that third row, and I'm going to keep the second row because all I need to do is just get rid of the 0, or the 2 above that -1 and turn it into a 0. So I'm going to do the row operation. 2 row 2 plus row 1 into row 1. That'll give me a 1 here, a 0 here, a 33 here, and then a 0 at the end. And then I guess if you want to change it into reduced echelon form, you need a 1 in that final spot. So we'd have one more matrix here. 1, 0, 33, 0, 0, 1, -18, 0, and zeros, and we get that by just taking negative row 2 into row 2 to create a 1 in that middle pivot. So now that we have the reduced row echelon form, we can move on to finding a linear dependence relation. That is finding a non-trivial solution to the homogeneous system. So here's our reduced echelon form, and this corresponds to the equations x1 is equal to 33x3, x2 is -18x3, and x3 is our free variable. So we're going to write x3 is equal to x3. So since x3 is free, I can get a non-trivial solution, a linear dependence relation, by picking any value that I want for x3, as long as it's non-zero, and I can get similar values for x1 and x2 from that choice. So note that if I pick x3 equals 0, that immediately determines that x1 and x2 are 0, and then that would represent the trivial solution. So let's choose the next easiest value other than 0. Let's let x3 equal 1. If x3 is 1, then x1 is 33, and x2 is negative 18. And what that means is that if I plug in those numbers, if I have 33 for x1, negative 18 for x2, and x3 being 1, that linear dependence relation is true. We can check it for the first row. 33 times 1 is 33. Negative 18 times 2 is negative 36. That's 33 minus 36 plus negative 3 would give us 0. And I see the mistake that I made here, so let's redo this a little bit. The mistake I made, and maybe you made the same thing, you didn't catch it. Here we have x1 plus 33, x3 is equal to 0. So that means that x1 is equal to negative 33x3. And x2 is equal to positive 18x3. So if we redo this, we can still let x3 equal 1, but in this case, x1 would be negative 33, and x2 would be positive 18. Plugging those in, we get negative 33 plus 18 plus 1 to be 0. Now if we check again, negative 33 times 1 is negative 33, plus 18 times 2 is plus 36. That gives us a positive 3, plus 1 times negative 3 is negative 3, and that does give us 0. And you can check the other rows as well. Note that this is the original columns of the matrix, not the reduced row echelon form columns. Or another way of writing this is negative 33 plus 18 plus 1, negative 33v1 plus 18v2 plus 1v3 equals 0. And that is just one possible linear dependence relation corresponding to a non-trivial solution of our homogeneous system. We could get another possible linear dependence relation by looking at another non-trivial solution in which there are infinitely many. Choose any other value for x3 and you get a different relation. So what we're talking about here is the linear independence of matrix columns. So here we had our linear dependence relation, negative 33 times the first column plus 18 times the second column plus 1 times the third column equaled the 0 vector. So that can be written as the matrix equation, the matrix A that we started out with, times some solution x is equal to 0. So here we have that each linear dependence relation among the columns of A corresponds to a non-trivial solution to the homogeneous equation AX equals 0. Those things are exactly the same. Similarly, we have that the columns of matrix A are linearly independent if and only if the equation AX equals 0, that homogeneous equation, has only the trivial solution. So the big part of this section 1.7 is that we recognize that when we're talking about linear independence and linear dependence, we are merely talking about the existence of non-trivial solutions in a homogeneous equation, which is 1.5 material. So when we're talking about linear independence, we do have some special cases that we can determine if a set of vectors is linearly independent with very little effort. We can just quickly realize that that's the case. So let's look at 4 of these special cases. First one is we have a set of one vector. So let's say we have one vector, v1. If you're going to ask if that set is linearly independent, you need to look at solutions to the equation x1 v1 is equal to 0. But that only has one solution, and that solution is x1 equal to 0. You can't multiply a vector by anything to get 0 unless it's 0 itself. So we say that this set is linearly independent as long as v1 is not 0. And maybe it's good to look at that. If v1 is equal to the 0 vector, then you can take any number times v1, and that would get you 0. So if it were the 0 vector, that wouldn't be the case. But if I have one non-zero vector, then I have a linearly independent set. And really, that's just not a very interesting set to look at, is what we're saying. Another special case is when we think about two vectors. So we're going to do two different examples here. We have the vectors u1 and u2, which are 2, 1, and 4, 2, and the vectors v1 and v2. We're going to ask if those pairs of vectors are linearly dependent or linearly independent. Do they constitute a linearly dependent set or a linearly independent set? So let's first look at the vectors u1 and u2. We may quickly notice that u2 is just 2 times the entries in u1. 2 times 2 is 4, and 1 times 2 is 2. Therefore, we can write a linearly dependence relation from this equation that I have. So maybe if I write this as 2u1 minus u2 equals 0, that's subtracting u2 from both sides, we get this linearly dependent relation. A set of non-zero numbers, at least not all 0, that give us 0 on the right-hand side. So this means that this is a linearly dependent set. For the second pair, v1 and v2, we can see that this is not, v2 is not a multiple of v1, because if it were, the first entries would be times 1, second entries are times 3. They have to be the same number to get a multiple. So we don't have the same case that we had in the first problem. But let's say that this was a linearly dependent set. And we can look at a solution, CV1 plus DV2 is equal to 0. And in this case, C and D both can't be, or both, if it's dependent, one of them has to be non-zero. So rewriting this, we have that CV1 is equal to negative DV2, and then we can write that as V1 is equal to negative D over C V2. That's what we have here. V1 is negative D over C V2. That is the case if D is not equal to 0. If D equals 0, then we have everything multiplied by 0 and things go wrong. Right? But this is not the case, because this means that V2 is a constant multiple of V1. Maybe a fractional constant, but it's still a constant multiple. And we just showed that that's not the case. So therefore, we must have that D equals 0. And then we can quickly derive that C must be 0 as well. And therefore, we have that the set V1, V2 is a linearly independent set. Because only the trivial solution, C equals 0, D equals 0, is a solution to that homogeneous equation. So examining this case a little bit deeper, we have a set of two vectors is linearly dependent if at least one vector is a multiple of the other. So here is an example of a linearly dependent set when we think about the graphical representation. Because we might have one vector here, v, and then if I take a multiple of it, there is 2v. Those are multiples of each other, so that is a linearly dependent set. On the contrary here, a set of two vectors is linearly independent if and only if neither of the vectors is a multiple of the other. So here we have our vector v, here we have another vector u, and they are not constant multiples of each other. They don't lie on the same line. So this would be linearly independent vectors. So what's nice here, we think about it graphically. Sometimes you're given vectors just in a graphical representation. And you can quickly recognize if two vectors are linearly dependent or linearly independent if we just think about, do they lie on the same line? Are they constant multiples of each other, or are they not? The third special case is a set containing the zero vector. Doesn't matter how many vectors I'm talking about, but at least one of them is the zero vector. So let's look at a set of vectors S here, V1 to Vp in Rn, containing the zero vector. We're going to say that that is always linearly dependent. And we'll do a quick proof of that. So let's renumber the vectors so that our first vector is our zero vector. Then we're going to try to find a solution to the homogeneous equation that is non-trivial. And we're going to do that by having zeros everywhere except for the first number, which can be anything. No matter what you take times the zero vector, you're still going to get 0 out. So this could be anything. Let's just say this is 0 or 2. And that would be a linear dependence relation because I have something that's non-zero. Note that the anything could be 0, and that would be the trivial solution, but something could be anything that's non-zero as well. So this shows that this is linearly dependent. So the special case is if I have a zero vector in the set of vectors that I'm talking about, that is automatically linearly dependent because I can get a quick dependence relation out of that homogeneous equation. The fourth special case here is a set containing too many vectors. And we'll talk about what too many vectors means in a second. So here we have, if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. Also said, we could say that any set of p vectors in Rn is linearly dependent if the number of vectors is greater than the number of entries. So p is greater than n. What we're going to do is an outline of this proof, and we'll say that if our matrix A consists of p columns with n entries in each column, this is an n by p matrix. N by p, n rows, p columns. And remember that the first column here is V1. That's going to go that entire column all the way to Vp. So this is n by p. There is more columns than there are rows. P is greater than n. So if this is the case, then Ax equals 0, that homogeneous equation, has more variables than equations. More columns than rows, which means that Ax equals 0 has non-trivial solutions because there must be free variables. If you have more columns than rows, you can only have one pivot in each row and one pivot in each column, which means that there's going to exist some column without a pivot, which means we have a free variable. And we talked about if the homogeneous equation has non-trivial solutions, that means that the columns of A are linearly dependent. That is an outline of that proof, that if you have more vectors than there are entries in the vector, more variables than there are equations, you're automatically linearly dependent because there must be a free variable and thus non-trivial solutions. So now let's look at a few examples and we'll test these quick cases out real quick. So we can determine if these are linearly independent or dependent by looking at the system of equations with a homogeneous system, row reducing and solving. But in this case, all four cases, we'll be able to quickly state if they're linearly independent or not by our four cases we just went over before. So in example A, we have two vectors, 3, 2, 1, and 9, 6, 4. We can determine the linear independence of two vectors by just seeing if they're multiples of each other. We can just look at the entries. So to get from the entries in the first to the second, we have to multiply by 3. we have to multiply by 3 here. So if the third entries, you have to multiply by 3 as well. This is a multiple. If not, they're not. And since this is times 4, those are not multiples. Since they are not multiples of each other, we have that this is a linearly independent set of vectors. Let's look at B here. B, we have the columns of this matrix. That is 5 vectors that we're going to look at. Right? We have the columns of this matrix that we could write as vectors. But instead we're going to look at it just as the matrix. Since this is the columns, we have more vectors than there are entries in the matrix. This is a 4 by 5 matrix. Therefore, if I row reduce this thing, I'm going to have a free variable. I can see there's going to be a free variable, and this means that this is going to be a linearly dependent set. Note that sometimes we're going to abbreviate linear independence with Li, and sometimes we're going to do the same thing, linearly dependent, as LD. Next one, we have 3 vectors, 3, 2, 1, 9, 6, 4, 0, 0, 0. Since I have the 0 vector here, this is immediately a linearly dependent set. No matter what other vectors are there, if you have 0, 0, 0, it's a linearly dependent set. And then our fourth one, we have just one vector, and we said that one vector is always a linearly independent set. So finally, let's characterize linearly dependent sets in a little more generality. And let's look at this example here. We have 4 vectors given in R3, and we can see them in the following diagram. So we have the vector v1 from the origin right there, the vector v2, the vector v3, and the vector v4. And we're going to ask, is this set of vectors linearly dependent? And to look at that, we're going to look at this plane that we drew here where 3 vectors are all on. Note that we could write v3 as 3v1 plus 2v2. This is 2v2. This is 3v1. So therefore, v3 we could write as 3v1 plus 2v2. And just from that little equation, we can say that these are going to be linearly dependent because I can now say that v3 is equal to 3v1 plus 2v2. If I subtract v3 from both sides, I can write this as 3v1 plus 2v2 minus v3 is equal to the 0 vector. And then maybe one more step here. Maybe I just have 3v1 plus 2v2 minus v3. And then since I haven't talked about v4, let's just add that in as well. Plus 0 v4 is equal to the 0 vector. This means that 3, 2, negative 1, 0 is a solution to x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 equals 0, the homogeneous equation. And this is a non-trivial solution since they're not all 0, so therefore we have linearly dependent set. Note that it didn't matter what V4 was at all, but since V1, V2, and V3 all were lying on the same plane, I could write one of them as a linear combination of the other. And that's what this theorem at the end is saying. If you have an index set S, index just means they're in order, or they're in different vectors, V1 to VP of two or more vectors, if that set is linearly dependent, we have that's the case if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is linearly dependent and V1 is not the zero vector, then there's some vector Vj that's a linear combination of the preceding vectors. That second part is just talking about that they're indexed, that they're written in order. But the key here is that if it's linearly dependent, you can write at least one of the vectors as a linear combination of the other. We saw with two vectors, that meant that, so if there are two vectors here, what that meant was that V1 and V2 were just multiples of each other. But if you get more and more vectors, you can say in generality that if you have three vectors, you could have something like V1 is CV2 plus DV3. You can say that. So three vectors. You could have something like V1 is equal to CV2, or something like V1 is equal to CV2 plus DV3. Both of those would mean linearly dependent. And once you have four vectors and more vectors, it gets more and more complicated. But all you need is one linear combination of vectors that's non-trivial to give us linearly dependent. And that's going to be a big talking point for our linear algebra course, is we can determine if a set is linearly dependent by writing one vector in terms of the other vector as a linear combination.